Welcome to the 2016 NASA Ames Summer Series. Evolution in front of us. So nature evolved solutions to various applications for thousands of years, and thus provides templates to mimic for our own applications. But when we try to mimic, we also gain insight on the original. Today's seminar, entitled Super Ball, a biologically inspired robot for planetary exploration, will be given by Mr. Vitas Sunspiral. Mr. Sunspiral received a BA in Symbolic Systems from Stanford University and an MS in Computer Science also from Stanford University. In 1998, he founded Mobot, which sold the world's first commercially available autonomous tour guide robot. He joined Ames in 2002 as a robotic researcher and is now a principal investigator for the Dynamic Tensegrity Robotic Lab in the Intelligent Robotic Group at NASA Ames. Please join me in welcoming Vitas Sunspiral.
Thank you, Jacob. All right. Let's get the presentation on the road. There we go. This is the one we want. All right, everybody, hello. Okay, so I'm going to give you an initial teaser here of where we're going with this story. This is the sort of NASA vision of this project, which is to build a robot that's so robust, so compliant and adaptable that it can survive landing on another planet as if it was its own airbag. So now you don't need an airbag, and you can explore in all sorts of new and interesting ways. And it has lots of mission design impacts. And we will get back to this in a moment with a lot more details. But I wanted to sort of show you where the current state of the technology and where we're headed is. But this all started with my own personal quest originally to really understand our intelligence. You know, as he mentioned, I came from the Symbolic Systems program, which is really a program that looked at a lot of human intelligence, artificial intelligence, and how complex systems like that work. And as I got into this over the years, I really started to feel that you needed to understand how we move if you want to understand how we think. These two are very tightly related. And if you really dive back into the origins of evolution, you'll see that the very first neurons appeared in order to control motors, i.e. the first muscles, early muscles. So the neurons are originally motor controllers, and then they evolved on top of that, and evolution happened on top of that. And as nature does, once it figures out a really good trick, it figures out how to reuse it and reapply it in more and more complex ways. And so if you want to understand, if you start by understanding how we move and really get that, then you start seeing the foundation for all these other more complex things we do, like the finer points of politics and art. And whether we like burritos or hamburgers and all that sort of stuff, right? So it's all related. So the story that I'm going to tell you today really involves starting with the brain. I'll tell you a little bit about that. We're going to start by tearing apart a lot of common assumptions. And that's sort of at the heart often of science. To learn new things, you have to often forget old things. And there's a lot of things that, you know, as science progresses, we're sort of discovering. And some of it is theoretical, and some of it is proven, and, you know, it's all kind of there in the mix. So we're going to start a little bit about the brain, and then we're going to dive into how the body works and have some maybe possibly surprising new insights into that. And that will bring us to tensegrity structures, which are a very interesting form of tensile structure. And from there, we'll get to the robots, and then back to the brain and the control system of how we actually move. And that will really lead us to some final philosophical insights. So, diving in. We generally assume that the brain is where we do all the thinking and all the reasoning and all the controls, and the motor cortex is where we drive all of our motion from. But it turns out this is not quite true. The brain does obviously have some very important roles to play, but people have been researching for quite a while the fact that if you remove the brain from an animal, what's called decerebration, or decerebrated animal, where they've severed the cerebellum from the brain stem. It turns out they can do all sorts of very interesting and complicated actions. Right? Everything from like they've put cows on tilt tables. This was done a long time ago, where it would resist the changing gravity field. You can see them walking. You can see them scratching. All this very complicated motions. And we've all heard about chickens running around with their heads cut off. And this is real. You can do it. You can go to a farm. I've done this and ended up eating a chicken. It is notable that the chicken with no head is no longer purposeful in where it's going. It's running randomly around. It doesn't have a goal. It doesn't have a direction, right? But it is coordinating hundreds of muscles and managing its balance on 2 legs. And that's a very complex set of behaviors to do. And the brain is mechanically removed, so you know that's not part of the solution. So this has been more formally studied, as I mentioned. I'm going to show you a video that was made almost a century ago by one of the earliest researchers into this field, who showed that locomotion can occur purely in the spine, from processes in the spine. Now, this is a video of a cat, so anyone who's going to be disturbed by that, it still has its head attached, but as I said, the brain has been removed. You can feel free to cover your eyes, but I always figure that since the science has been done, we might as well learn from it. So hang with it if you can. So what you see in this video is that the cat, as the treadmill goes through different speeds, the cat will express 3 different types of gaits. It will go from a walk to a trot to a gallop. And we know, again, as I said, that the brain is not involved in this. This is purely from the spine. And the spine is interesting. It's decentralized. It has, each vertebrae is its own little node of neurons. And so it's this segmented, modular, decentralized system. So there's not some central CPU, there's not some motor cortex in the middle of the spine that's coordinating all of this. So you're getting this coordination out of a decentralized system, and that's a very, very important clue, and we're going to come back to it a lot later on in the talk. So that's my teaser for the controls, and to get you out of maybe your comfort zone of thinking of how the brain might be at the center of everything. We will get back to it at the end of the talk, but to really dive into understanding all of this, we also have to look at the body and understand how it functions. Right? No matter how smart your control system is, you can't make a brick fly. Right? You have to combine both the structure and the controls together in an intelligent way. So you may have had this skeleton in your classroom, biology classroom in elementary school. Very useful initial insights to it, but it's telling you a lie. Right? You look at this and it leads you to think that the skeleton is this thing, this like structure, kind of like the rafters and the infrastructure of a house, the walls and the roof and the ceiling joists and all of that. But actually it's held together by a bunch of aftermarket pins and hinges that don't exist in reality. If it was really just a bunch of bones, it would be a pile of bones on the floor. Right? What holds our body together is all of the soft tensile material, the muscles, the ligaments, the tendons, right? Collectively often called the fascia. And what you'll see here in this MRI video on the side is that the bones don't just move around a single axis hinge like is often assumed. If you think like, oh, my knee, it's a hinge, right? Just bend it. Actually, what you see is the bones do a very complex gliding and sliding motion because they're not just pin hinged. There's no pin holding it together. It's the soft material that holds it all together and allows for very complex multidimensional motions of the bones relative to each other. And that turns out to be very important. It looks like from the outside a very subtle difference, very easy to say, okay, this is just a hinge. But if you actually start looking at how forces flow through the structure and what becomes possible when you have all of this complexity and freedom of motion between the bones, it opens up a whole different design space than we are accustomed to using in traditional robots. So, as I mentioned, this soft tissue, we're going to dive into it more, is often, again, sort of collectively known as fascia, the connective tissue. It was often ignored early on in anatomical studies, right? People looked at, oh, it's the muscles, it's the bones. These are these simple segments, and we cut all the other stuff apart. The tendons are just connectors between the motors and the bones. Well, it turns out that the fascia is actually a continuous system. Unlike the bones, which will just end up being a pile on the floor, it's the fascia that is continuous from end to end. It is the outer layer of your bones, the periosteum, is a bunch of fibers, and those fibers are continuous with the fibers of your tendon. And those fibers are continuous with the fibers that are all through and around your muscles. And in fact, when you start off as embryonic, you start off as a mass of fascia, as a mass of soft tissue. And it's only later during your development that the bones start to harden into the pockets. Muscles and bones grow into the pockets in the soft tissue. So this soft tissue is the fundamental form of your body, and bones and muscles come later. Very important. So people have been studying this. There is Tom Myers is one of the researchers and who's looked a lot into mapping the long distance chains of soft tissue in the body, and he's worked with a bunch of other anatomists, sort of a new revolutionary way of doing dissections in anatomy, and they work with unpreserved fresh cadavers, because when you take formaldehyde and you preserve a cadaver, it binds and hardens all the fascia together, and it loses some of the key qualities that matter in a living body. Right? So they've been doing these dissections and trying to follow the long lines of fibers in the body. And what you see over here, for instance, is the continuous connection from the trapezius, sort of the muscles up here, all the way down to your fingers. That is one system. And it's actually continuous with the rest of the body too. Right? But that's just one segment that you can go look at. And so now you start thinking about the tensile connections and pathways in the body as being the primary way that forces and loads are transmitted through the body. And those are important, right? When you move, you step, when you push on things, those are all forces and loads that you need to move through the body in different ways and control and manage in order to be able to walk and move and carry things in the world. So what's really interesting, and this becomes much more speculative, is that Tom Myers, he calls one of his books Anatomy Trains. He's mapped out a number of these long-distance pathways, and he finds that they end up looking a lot like the meridians of Chinese acupuncture, right? And so that's interesting. There's some research that sort of indicates that, again, it's along these pathways of tensile load-bearing that you get your primary proprioceptive sensors, all the strain gauges, the Golgi tendon organs is what they're called, and other sensors that tell us where and how our body is moving and dealing with forces tend to concentrate along these pathways of load transfer, which makes sense. That's right where the loads are, that's right we need to measure things. And so it is possible that that's part of what acupuncture is doing, is starting to play with these sensory inputs to ourselves and therefore jiggle with our control systems in interesting and unique ways. Very speculative at that point. So, now having sort of introduced this idea of the body as primarily a tensile system, it obviously does have bones in there, they are playing a role. I want to just sort of point out, like, what are we used to building? We're used to building things like this house on the side of the picture here, this building. We build static objects that are load-bearing, we call them continuous compression structures, right? The load of the roof rests on the walls, and that passes to the next floor down, and it accumulates load all the way down to the ground. I used to work with this robot that was built down at JPL, Jet Propulsion Laboratory, and it's called Athlete. It was designed to carry lunar habitat infrastructure components, big pieces of hardware on the moon where you don't have forklifts to take it off the lander and all of that. So it was able to walk and roll, do all sorts of amazing things. It has 6 legs with 7 degrees of freedom in each leg. And the most recent version of Athlete was, I think, 6 meters. It could spread its legs up to 6 meters wide, it could stand 4 meters tall, very big robot. And I was working on walking algorithms for it. And this robot can do amazing things, right? It can climb over complex cliffs and ledges. It takes all day to sort of figure out every little detail to make it happen, but it could do it, right? Really capable robot. And yet there we were sometimes in the Mars yard, which is their flat dirt yard where they do rover testing. And it would be on what to the rest of us would appear essentially flat ground and dirt ground. And suddenly one of the ankles would be completely saturated, like over-torqued. Couldn't do anything. We had to sort of reposition the whole robot until we got the loads off that ankle and we could move again on flat ground. And what I came to realize was that because it's a rigid structure, there's this rigid pinned connection between all the components, you were able to get 6-meter-long lever arms internal to the structure. So even if you stood on some small little lump of dirt, that could be enough with a 6 meters of leverage to cause enormous torques and loads to enter into the joints. And this is one of the core limitations of sort of a traditional, rigidly defined structure. And if you really want to think about it in a more sort of philosophical perspective, these kinds of rigidly designed systems where everything is sort of connected together, the way we build our houses, they're really good for building static structures, something that's going to sit still. You define all the load paths, you know exactly where it's going to go, you put the materials exactly there, it supports the loads, boom, you're fine. And then we've taken that concept and we started adding motors to it and say, hey, look, we can make moving structures. But it's the wrong structural concept for something that's intended to move. So this is what brings us to tensegrity structures. Tensegrity is a word coined by Buckminster Fuller. It comes from tension and integrity. And it is this structural concept that looks at the tensile network as the primary system for integrating the whole structure. Right? So you get these very interesting art structures where these rods are just floating in space and they're held together by the tension network of cables. Very fascinating, very sort of awe-inspiring. You can, if you're local, you can go to Stanford, and there's one of them on the campus there. So I think maybe my years there made it sort of intuitive to me that such a thing would exist, and it was sensible. But it's very counter to our traditional way of thinking about structures. They have a number of really interesting physical properties, now that you've sort of switched around how things work. One of them is that they have a very high strength-to-weight ratio. Right? The materials are either experiencing pure compression, those rods are being squeezed by the tensile network, or the cables are experiencing pure tension. So you don't need to deal with bending and shear forces to the same extent you do in a traditional mechanism. You don't have internal lever arms where you are magnifying the forces into joints, like I showed on that JPL robot, the Athlete, which is a great robot, by the way. You're not magnifying those forces into those joints, so you don't have to massively oversize them to deal with all the forces that accumulate. Instead, these structures have the interesting property of distributing and diffusing applied loads. You see on my little chart here, if you push down on one of those rods, that force actually propagates and diffuses through the whole structure such that all the cables and all the rods participate in absorbing that stress, and it spreads it out. And this is something that you see in our bodies too, right? We do amazing things because we are able to use our whole bodies to, hold ourselves in strange and awkward positions. I'll show some images of that later. And another thing that's very valuable about these is that they have tunable stiffness. Then you find this in modern robotics as we take robots out of the lab and we try to get them to move in real-world situations. How stiff you are is very important, right? If you bump into something accidentally, you want to be soft. You want to not break the podium or yourself, right? You want to comply to that. Yet at the same time, if you want to pick up a heavy load, you need to become a little rigid to do that. Otherwise, you're just going to be floppy. You're not going to be able to get anything done, right? So you need to be able to change your stiffness in order to do different things. As you move across different soils, different terrains, you need to change your stiffness to adapt to the type of terrain you're on. If you're on hard soil versus sand, you actually want a different stiffness in your body so that you can move efficiently. And these structures enable that because they are pre-tensioned. You can tighten up all the cables and the whole thing becomes stiffer. What's interesting about it, though, is that these structures are hard to make static. If you look at those art structures that I showed you on the last slide, people have talked about this in architecture world, like, oh, we can make buildings out of this. And they're like, well, they're not great at static structures. They always want to oscillate. They always want to move a little bit. And we'll come back to this when we get to the control section. But it's an important quality. These are structures that want to move inherently. It's quality of the system. So that seems to make sense as something you'd want to do if you're going to build a robot that moves. Other interesting clues we have is that there are a number of researchers who've been looking at tensegrity systems in biology. So we have folks like Donald Ingbar at the Harvard Weiss Institute who has spent the last 20, 30 years looking at cell structures, the microtubules and microfilaments in cells, and seeing a lot of similarity to the tensegrity systems that we build as humans. And so he's built various models of them. And there's other folks who are looking at our gross physiology as tensegrity structures, right? So spines and knees and legs. And spine's a really interesting one, right? I have this model in my lab, or a similar model to it, and you can compress it. You can put load on it, and the vertebrae don't touch. All the forces pass through the cables, right? And it can still hold itself up, and all the vertebrae are kind of floating. And this is really compelling, right? It's not an exact model of how our spine works. It's abstracted and simplified, and there's a lot of research still to be done here. But one would wonder, if you take the traditional view of our spine being a stack of vertebrae and discs, why don't we all have bulging discs? Why don't we all have pinched nerves? Right? One of the arguments that I make is that because primarily the loads and forces should be passing through your muscles and your tendons and ligaments. And it's when you get out of balance, when you've been spending 10 hours a day sitting, working or in front of a television or in a car, that you are starting to get a dysfunction in that balance of tension and no longer keep those vertebrae floating separately like they should be. So this story goes a lot deeper, but that's just to give some ideas of what's out there and what's possible. So taking all of that inspiration, I'm going to show you a little bit of the robotics work that then we're doing here at NASA with this, to explore this possibility as a way to design the future robots. And then we'll end up talking about how we can control them. So again, SuperBall. Right now, we build robots and then we pack them in these with various landing systems, airbags, sky cranes, whatever. Very complex systems that you use once and then discard. It's a lot of mass that you've wasted. I mean, you need it because that's the critical moment, but could you get away from that? And so what we're showing here is, in this very first prototype, we actually designed this prototype to really explore how it can move, how it can roll. So we really put a lot of focus into just the mechatronics of designing the motors and actuators and controls for it. And yet, despite that, despite not really focusing on the landing part, we were able to, as you see, drop it off of even just 1 meter tall loading docks, which most robots of this size don't handle very gracefully. So that's kind of where we are. And what's interesting is when you build this kind of robot, something that could land from orbit safely and not break, it also changes how you explore another planet. There's lots of places we want to go where the science is not necessarily in the easy place, right? I mean, nice big flat fields, you find a rock, that's great, right? We can do that with our rovers today. But science isn't waiting for us where it's easy for us to go. We need to build the robots that can handle the risky and dangerous places where the good science really is. And so, for instance, we want to explore places like Europa, one of the icy moons that may harbor life under that crust of ice in its subsurface ocean. We speculate that the surface may be very, very jagged and complicated tumble of ice blocks that have broken and refused and whatnot. We don't really know yet. But it could be a very, very difficult environment that a traditional rover would not do well with. So we want to be able to send a robot there, or anywhere, where there's an inherent risk of it slipping, an inherent risk of it falling, right? That could happen if you're going to go somewhere that's more complex than an easy flat terrain. And so if that happens, what robot's going to survive that? That's really the quality you need to look at, the structure of the robot. How is it going to survive the unexpected? Right? You can plan all you want, but if the soil turns out from underneath your foot and you fall, what happens next? And so building the robots that can handle the risk of real rough, real-world situations is sort of one of my motivators in all of this. We started doing this a couple years ago with some funding from the NASA Innovative Advanced Concepts Program, which is a very sort of early stage new ideas program. And I started by building a physics-based simulator, NTRT, the NASA Tensegrity Robotics Toolkit. This has actually been open sourced. You can find it on GitHub, and you can use it. You can participate in the community that's using it. And we have made it easy to design new tensegrity structures. We've integrated all sorts of machine learning techniques and some of the neuroscience-inspired control techniques that I'll mention later, and really sort of built it up as a system that can allow for the exploration of both form and structure and locomotion and movement, and really to try to be a touch point for a community of people interested in furthering this arm of science. And of course, it is an ongoing project, so it can always use more help too. And so we did various studies, right? So this is one study that just showed that you can take this structure and you can pack it flat and then deploy it, turn it into its full shape. And that helps you when you're launching stuff into space because it all has to fit into a rocket. So anything you can pack small and then deploy is helpful. You can put a payload in the center of it where that ball is and really protect that. That ball ends up acting like the key elements inside your airbag, right? So you can make sure that your sensitive instruments are safely protected on landing. It can roll over a variety of complex terrains. It's kind of like a ball. It kind of has that spherical rolling thing, but it also has feet, if you will. So we call it a punctuated rolling. It's an interesting hybrid between rolling and walking. So there's a lot that it can do. And then it also, I've shown that you can remove one of the cables that would normally have been there, and you can still get the whole thing to hold together and roll. So it's redundant to some of these failures that might come up. And we did some early prototype testing. This was with some students from University of Idaho. They built various prototypes. They put accelerometers in it and started dropping it and gathered the data and found that it matched our analytical models. So it really gave us confidence that the physics-based simulations we were doing were holding up to reality, and that, okay, this is reasonable to do from a structural perspective, that you could land at 15 meters a second and survive. So then the next question is, can you make it move and also have that whole structure land at 15 meters a second and survive? So we started building various prototypes, and in that prototype there, we actually put it in a motion capture system and again compared it to our simulator to say, okay, look, the motion controls that we developed in simulation seem to be holding up in reality. And then that led us to the Superball prototype that you see now, which is our current prototype that we're working with. It's not a full prototype. It's kind of got half the actuators that we'd like it to have, and there's already many lessons we've learned that we're going to hopefully fix in the next version. But this is how science goes. You start with what you can, and it gets better over time. We looked at putting payloads in it and controlling where the payload is. So even if you have an instrument in that payload, you can drop the payload down to the ground and take direct samples of the soil. Is one of the things you can do. And now that we understand how to do a lot of the basics of locomotion with this robot, we also are now under the Game Changing Developments program pushing this along, really pushing things like how do you understand where it is in space? Right? On a traditional robot, you can put a sensor here that tells you exactly what angle the joint is at. Although again, this is not a normal robot joint, but here we started, it's a little more complicated. You've got all this freedom of motion between the bones. So how do you tell where they are relative to each other? How do you manage to sense its overall state? So we've pushed that algorithm forward, and now we're working with some collaborators at UC Berkeley to use some of their advanced machine learning techniques to figure out how to get this to move. Right? I showed you a lot of stuff in simulation, and we used evolutionary algorithms and other sort of machine learning techniques that took 10,000 iterations to complete, which is fine in simulation, but on a real hardware robot, you need to do it in a more efficient manner because 10,000 iterations might become a little tedious or otherwise threaten to break your robot. So what you see here is a really sort of funny, jangly movement. It's almost like a baby learning to walk. It's randomly moving itself around, and from doing so, starting to discover its own dynamics. And that's part of this algorithm that we're working with from Berkeley, the guided policy search algorithm. It actually helps learn in a very, very few experiments on a hardware robot how to move through optimal trajectories and then how to generalize that to a broader class of motion strategies. So that's kind of right where we are in the control state right now. We've gotten a little further than this. I'm just not showing the most recent videos. And then, as I mentioned, we're making the next prototype, and we hope to do this over the course of the next year, Superball 2.0. Our intention here is to really now take what we understand about how to make it move and make it robust to landing, and we're going to start rolling this thing off the roof of buildings and have it survive. That's my hope. And if that works, it'll be fun. And that's just the beginning, right? And then we're going to throw it at other planets eventually, right? So you can't be shy. One of our other collaborators is at Rutgers University, and they've been looking at how do you do long-range motion planning, right? So you understand the dynamics, you can get it to roll, but what if you want to do really complicated movement and get through complex terrains? And so they've been using some really advanced kinodynamic planning algorithms to look at how would you plan a complex trajectory through there. So that's sort of the state of Superball, but Superball is really just the first of what many possible robots could be. Again, this is a structural concept, it's a design approach to robotics. And so one of the things we look at when you look back at humans is that we move from our core, right? Look, this is going back to like, how do people do this stuff, right? I mean, I can't. I can do a handstand, or at least I used to be able to, but, but that's crazy. And you talk to any athlete, and again, it's from the core, from your spine and all these core muscles. That's the source of motion. Yet, you ask an amateur to pick up a tennis racket, and they swing from their arms, right? And then the expert learns to drive from here. And so you look at our robotics today. What do? We spend a lot of time, if you look at legged and armed robots, we spend a lot of time building really complex, compliant, adaptable arms and legs, and then bolting it to a rigid box and calling it a robot, right? Great place to start. We have to start somewhere, but obviously that's still amateur, right? If we want to have really excellent moving robots, we need to get to the point where we can understand how the spine works. So you can get that dynamic, flexible, and powerful motion. Now, the challenge is, in a traditional robotics control approach, how do you control so many degrees of freedom, so many flexible joints and all of that? It's just like, it breaks all the rules. It makes the algorithms really, really complicated. But again, can't be afraid of things that are hard. Started exploring this, really looking at this tensegrity spine model and exploring, well, what can we do? I want to put arms and legs on eventually, but let's just make it look like a snake at first and crawl around just to see how do we get this to control motion. And it's been a very interesting path, right? What we found is that these are very nice, adaptable, flexible systems. They respond well. They integrate forces from wherever you apply them. And we started using, and I'll talk more about this in our control system, these ideas out of neuroscience, central pattern generators. They are rhythmic controllers. That this spine actually has no central control whatsoever. Each string has its own individual controller, and they're all oscillating in a certain way such that you get this uniform behavior of locomotion. And then we started exploring around in our simulator different structures, right? If you change the design of the spine from that first tetrahedral complex to these more interesting sort of vertebrae-like systems, and then throw our machine learning algorithms on top of it and explore it until it kind of finds an optimal locomotion pattern, what do you get? And so it's this space between structural design and controls where you can really start exploring what's possible. And so then we added ribs to it. And just sort of no direction on how this thing should learn, we added ribs and it started slithering. I thought that was interesting. And then, of course, you could always, again, you always have that fear that you're doing stuff in a simulator and it's just pretty videos. So we built a little prototype robot and found that we could use the same controls that we were learning as some of the earlier tetrahedral ones, and we got very similar motion. So again, we feel confident that there is some reality behind those videos that were built in the physics simulator. So spines were a place to start, and now working with some students at UC Santa Cruz, we were going a little bit more directly towards what we want, which is actually a quadruped robot, a legged walking robot. This is what's going to really enable someday the ability to clamber around on complex terrains like a mountain goat does, right? We can go anywhere, right? It's like, there's science, let's go there. Okay, we got a mountain goat, let's do it, right? And what do you see in this quality? This is just sort of passively being poked right now. This is just the passive structure. And it has exactly what you want, right? It is a stable structure. It's able to hold itself up. And yet at the same time, if you poke it, if you prod it, if you drop it, it responds, it adapts. It's really nice and compliant. And so we took it and then in the simulator dropped it onto a variety of random block fields. And what we found is that it adapts really nicely. I especially like this one over here, where it's on this sort of cross body of blocks. And that's just it passively and naturally redistributing its load and rebalancing itself. No control is used to make that happen. And it's possible, right? A normal robot with a rigid torso would fall over in a situation like this. This is possible because of the flexible spine. It allows all the forces of contact to be integrated, twisted, rotated, whatever needs to be done. And that's what you're really going to need if you want to be able to clamber over really complex things and, stem up some rock face and still control how your forces are pushing into the ground so that you don't slip and fall. Other folks at UC Santa Cruz that I collaborate with are also then looking at arms and legs and shoulders, right? Our shoulders are really amazing joints. These are big spherical joints with really complex ranges of motion. So they're trying to explore how you can build robots that take advantage of this tensegrity principle and give you those ranges of motion. But as I said, that's sort of the far future, early sort of research, mostly in collaboration with other folks to see what's possible. But the other big question is, how do you control these things? And as I mentioned at the beginning, these structures are oscillatory. They want to move, they vibrate. If you go to that big art structure at Stanford, the tensegrity structure, and you happen to be there late at night and you push on it rhythmically for a while, you'll find this thing that looks pretty static and is pretty giant. It starts moving, right? You're like, okay, maybe I don't want that for my house, right? So how do I control this, right? If you talk to your average controls engineer, maybe an airplane designer, they'll be like, oh yeah, oscillations, those are bad. Yeah, we don't want any of those in our structures. They make the plane explode, right? And they're true. Uncontrolled oscillation is a really bad thing. If you can't sense it and you can't control it, that causes trouble, right? Then you can get into runaway oscillation and resonances. But if you can control it, if you can sense the oscillation and you can control it, there's a lot of very interesting things you can do with it. And beyond just the oscillation, these are complex nonlinear systems that really sort of a very limited design and engineering tools for. So we're really sort of at the beginning of figuring out how to make this all work. So again, let's turn to biology. Everything we do is rhythmic. Very basic things, your heartbeat, rhythmic. How you eat, chewing, is a very rhythmic thing. How we talk with each other, everything from the phonemes, the basic sounds, those are frequency-based, to high-level dialogue. If I started talking very randomly and differently, you'd think it was kind of weird, right? Rhythm matters to how we even engage with each other. Dancing, we love that. Singing, walking, the basics of motion, all these things are rhythmic. And then the most important of all, your breathing, I hope. And therefore, everything you do is rhythmic. So here's a quick experiment for you to try. So let's also keep you awake. Sort of sit up a little bit so you're not slouched into your chair. And stick a finger out. Maybe don't poke anyone unless they want you to. But point your finger at something. And you think, OK, now look, I'm going to hold my finger still. And that's not rhythmic, right? Look, I'm holding my finger still. Now, take some deep breaths. And keep holding that finger still. Notice your chest. Notice your upper body. It's moving as you take those breaths. So even though you're holding your finger still, your arm and your upper body, all those muscles are having to actuate and organize themselves in a rhythmic manner to counteract the fact that you're breathing. So the very fact that you can hold yourself still, or at least some part of your body still, requires rhythmic control. Because you're breathing, everything is rhythmic. And I really hope you don't stop breathing. So here's another experiment. If you guys could all clap together in unison, I'm not going to lead. I'm not going to show you how. I think you can do it. Go ahead and give it a try. Just start clapping in unison. Thank you. Thank you. I like to get that done early, says I don't know what's going to happen at the end of the talk. But this is interesting, right? No one was telling you how to do that, and yet you did. So this turns out to be a really important principle, that rhythmic things that share some energy can synchronize, can come into a coordinated behavior. So this is everything from, let's get both of these going. Everything from metronomes on a table, right, that get randomly started, to this is sort of a simulation of fireflies flashing. And there are fireflies in nature that do this, where they all flash in unison, right? And the fireflies, they don't share a clock. They're not on an atomic clock. They don't have a king or queen firefly. There's no common bus. They're just flashing. Yet they can synchronize and behave. And these metronomes, what's happening here is they're moving, but they share some vibration through the table they're on, physical vibration. And because of that small, minute amount of vibration, they will eventually all synchronize. So this is a very important property. It's been studied. There's a mathematician at Cornell, Stephen Stogartz, who's written some really good books about this. One of them is called Sync, How Order Emerges from Chaos. And this is a very, very fundamental principle. It's a mathematical principle independent of the physics of implementation, right? As you can see in these two different videos. That rhythmic systems that exchange energy can synchronize. And so you find this all throughout nature. And it's a really important thing because we often hear about entropy and how everything is tending towards disorder. And then you ask ourselves, why are we so organized? Maybe my house isn't organized, but why, we as living things are highly organized systems. How does that come around if entropy exists? Well, it turns out that because rhythmic systems can create order with no central control, no top-down management, but purely as an emergent mathematical property. So we find this. I'm not going to wait for that to synchronize. Well, this here. I'll just show you that at the end of the video. It is. Come on, do it. All right. Yeah, there they are. They all got there, right? So, these algorithms are understandable. There's you can go find lots of people making synthetic algorithms for synchronization in distributed manners. So it turns out that this is at the heart of modern neuroscience, Right? You got people like Giorgio Buzzacchi who are really saying that brains are primarily concerned with rhythm, timing, and temporal prediction. And this makes sense. If everything is rhythmic and all the other animals are rhythmic, then you really want to be able to track other rhythmic motions, right? The sun cycle is rhythmic. When a particular tree is going to become ripe with fruit is rhythmic. If you're the leopard sitting in a tree branch waiting for the gazelle to pass underneath, and you want to jump on it, you better understand the rhythm of its motion and get your timing just right. Otherwise, you're going to face plant and miss lunch. Right? So rhythm's at the heart of it all, and we see this in neurons. Right? They are rhythmic, bursting, oscillatory systems. Besides individual neurons, you have networks of neurons that are called central pattern generators, CPGs. And this is at the heart of a lot of modern research into mammalian locomotion, that these networks of CPGs are able to create rhythms and generate them and then interact with each other and coordinate the control of motors, i.e. muscles, and be at the center of a lot of gait production, and a lot of the rhythmic motions that we do, everything from chewing to walking. So why are CPGs interesting then? They have a couple interesting properties. Right? If you have this distributed system that is able, from its own intrinsic dynamics, to be able to come up with an organized rhythmic behavior and coordinate its actions, then you get a reduction in dimensionality of control. Right? So what would normally be hundreds of degrees of muscles that need to be coordinated, you can simplify that down to a much simpler problem. And one of the things that I see in tensegrity structures and in CPGs, if you dive into how that control works, how information passes through a network of these rhythmic controllers, it ends up being very adaptable and compliant in much the same way that these tensegrity structures are adaptable and compliant to the forces they are experiencing. So in terms of that reduction of complexity, here is a 30-segment spine that's running using a bunch of these CPGs. Each cable has its own CPG controller. For reference, a dog has 32 segments in its spine. So this has overall 232 different individually controlled muscles. If you try to do this with traditional inverse kinematics or other forms of robotics control, you would just break every machine you could throw at it, right? It would be way too complicated. That's why you don't see robots with complex spines. Yet here we are controlling this computationally very efficiently because it is a distributed, very simple form of control that allows its coordination to come as an intrinsic property of its rhythm. So then the question is, you can push this out, you can use a bunch of sine waves to make these rhythms and have them move in that way, but what's more important is when you close the loop. When you take your, up at the top we have the actual low-level controllers, you have the physics model at the bottom, you get some sensor information about length, tension, velocity, and then we pass it through a very simple neural network to close the loop back into that CPG. So now that you start actually getting feedback from the environment. And what you see here right now, the feedback is off. This is what we'd call open loop control. We're just sort of commanding the robot to move. And when we turn on the feedback, which just happened, you'll see that its gait cycle changes. And now you start getting a gait that's a much larger amplitude gait, and it's really tuning to the coupled dynamics of the robot interacting with this environment. And that's that natural tendency to just couple with the environment and with the actual structure itself, which makes this control approach so flexible and dynamic. You don't have to understand the external reality perfectly. Rather, it's just based on the forces and experience of its own motion, it's going to find an efficient way to continue to move. And then we have the final question of, that's all great, you got these robots moving, they're moving across fields of flat ground or lumpy ground or whatever, but how do you do something? How do you actually make it go accomplish some goal? And this is where the brain comes back in, finally. Right? The brain that we took off at the beginning, we actually start putting a layer of more artificial neurons on there where we start looking at a goal and start saying, what's our direction to that goal? And using that to influence how the central pattern generator works, right? And what direction it's going. And what you'll see, start all these videos, is that across a variety of different terrains and a variety of different goals, we eventually were able to get these robots to drive to these goal targets. And it's just pretty much doing a steering. It's not trying to control all the individual muscles like you would on a traditional robot. Rather, we're saying, go a little more left, go a little more right, the goal's over there. That's where we're trying to go. It's kind of straightforward visual servoing, if you will, but with a very complex underlying distributed system that manages all the details of the physical interaction with the environment. So you don't have to do that all in your brain. my head would hurt if I had to think about every little bit of force and contact that I needed to control in order to operate this computer, for instance. So that's the big part of the story, and it brings us back to the brain, right? And this is where we get to the fun part of it all. Why do science if you don't have philosophy? And which is this. We tend to use the current technology of the day as our model for how we think about things, right? So we tend to think about our brains like the CPUs of our computers, because that's today's technology. But what this talk hopefully might have shown you is that you have a computational system in your head that is perhaps built around synchronization rather than on binary logical flows. Right? The fact that we can do math is amazing, but we don't necessarily use math at the basis of our brains, other than the fact that synchronization is a mathematical property. But so what are some of the things that come out of this, right? If you have a system built around synchronization, you see qualities that are very hard for us to accomplish in traditional AI techniques. Everything from pattern recognition, seeing a bunch of things being similar, right? It's very hard. Some of the deep learning algorithms of today are starting to be able to accomplish this. But associations, like connections, what do humans love to do? We love to connect with each other. We love to make new friends and just resonate with each other. And what else do we do? If you move somewhere, if you say move to Georgia and live there for a few years, you would pick up a Southern drawl. It's almost impossible to stop. We synchronize with the people around us. We become like the people we hang out with. You develop a new group of friends. You might start dressing like them, putting on funny party hats, whatever they do, it's a very good chance that you share a lot of the same political views as the people that you love and trust the most, right? It's just part of what we do. We synchronize with those around us. So we start seeing a lot of these qualities that are very human, high-level social interaction qualities having the same underlying drivers as we see in the basis of how do we move our bodies through the world. This quality of rhythm and synchronization, and the fact that we like to dance, unless we're too embarrassed by ourselves, but that's its own problem. Anyways, that's the philosophy behind all of this. Hopefully it also helps us go explore the solar system. And I did not do this alone. Here are at least a small portion of the people who have helped me along the way. These were students from summer of 2014, and I really need to make a new photo of that this summer of all the other new people who have really helped out building this vision. And so thanks to all of them, and a thanks to you for listening. And that's my talk.
Thank you. Great talk. So we have time for a few questions. If you have a question, please raise your hand, wait for a microphone, and then ask one question only. Okay. Right there.
I am so delighted to hear all of this. I thought that nobody else in the world was thinking about brains and bodies and oscillators and stuff in this way. And you're way closer to the ground truth. You're actually building it and it's working. My approach is information science, theoretical physics, and algorithms and stuff like that. So I've been working in the Valley. So I'd like to offer a couple predictions. I know far too much about it to call them the questions, about where this project is going and why it's going to be so wonderful. It's exactly the right way of taking it apart. Tensegrity is a beautiful sort of thing. And when you make it big enough, it paradoxically gets simpler. You were talking about 232 classical robotic sort of hinge variables down to 30 segments. Well, once you get like a zillion segments, it's now just a three-dimensional structure. So you're going to find yourself solving continuous equations as if it were Gumby, and continuous vibrations. The other prediction is that you're going to find all the interesting stuff at the very highest bandwidth. When you look for central pattern recognition, that tends to synchronize, and it's kind of slow. There's not much information flow in a pendulum once it starts swinging. But all the tiny little ripples from our million mechanoreceptors and our million muscle fibers, it's like a 3D tomography problem with, a million little firecrackers going off, and the brain has to gather all those vibrations somehow and make sense of it in 3D. So ultimately, once you solve that, you're going to understand yoga, you're going to understand acupuncture, because you're going to understand bodies as megahertz level vibrating instruments. And you can hear the tremor in my voice, it's kind of obvious, right? But you'll also understand our communication, not as merely the syncing of pendulums, but as chaos control ripples in which the very vibrations from inside my body are being felt by everyone.
Thank you.
I had a question regarding the motion. How do you control, have you tried a downhill motion of the robot? Because it seems unstable right now, because it's pivoting at 1 or 2 points and it's just rolling down. So have you already figured out how you'll control the downhill motion?
Yeah, so the way, like, I showed you both rolling it just downhill in a passive way, and then I also showed some videos of it just rolling over on flat ground. And the way Superball is locomoting right now is that it is moving its center of mass over the polygon of support of its feet until it falls over. Much like us, I mean, we move by falling over our support base and then catching ourselves. So it has that similar quality of moving its center of mass and then causing that to be a dynamic motion. So if you want to slow it down while going downhill, you would want to move your center of mass towards the uphill so that you could, control that slightly. Now, that being said, it may not be the best at really having controlled descent down a really steep hill, but the thing to remember is that this is a robot that hopefully will safely fall from orbit. So if it tumbles down a hill in a somewhat dynamic manner, it is not necessarily going to be the end of the mission like it would in a traditional rover, right? This is going to be something that it could handle as a structure. So the other point to remember is Superball is the beginning. And I think in and of itself, it has some real potential value exactly as it is as a flight mission when we have continued to build the technologies further. But there's a lot of variations you could build on this, right? Instead of just being 6 bars, you could have a version of it that has 12 or 30 bars or whatever. And then that starts becoming more like a real sphere that you can deform even further. And you could flatten it down to look more like a tread or change its body shape and change its ground contact surface a lot more. That's obviously a much more complicated mechanism that would stretch the limited budget that I've had in terms of building it. So we're working with the simplest one we can possibly make that has a fewer number of motors and components in it. But down the road, we will be opening up that exploration, which is also why I'm exploring the legged robots, because they will have even better abilities to manage complex terrains than Superball has. And so somewhere in all that design space will be the perfect balance between shock absorption for landing and trainability for exploration. And when you get to the trade studies of what do we want to do for a particular mission, that's when you start sort of figuring out where in that design space you really want to go.
Right there.
Hi. So my question is, like, based on the projects you work on with the Superball, what's your ultimate goal? Like, with the project, are you trying to send up into space and collect information? I'm just curious to know what's your ultimate goal.
Well, you know what? I figure why limit yourself to one goal, right? Embrace the power of and. It's all of the above, right? I definitely would love to have this mature to the point where we have a whole new approach to doing exploration of the solar system, and we can and bring this technology to service in that way. And at the same time, as Jacob hinted at the beginning of this, the very quest to understand these things, the very quest to imitate or be inspired by biology is also very informative about ourselves. And if we come away with new ideas and new understandings of how we work. I mean, a lot of these theories I've shown you about how the body works, how the brain works, they're out there. They're being discussed and debated in different scientific communities. But if we can then say, hey, look, this is why it makes sense to have a body that's not rigidly connected. This is the advantages you get because I can build robots that can do things no other robot can do. That's going to tell us something about how human bodies work. And that may inform how surgeries are done and how healthcare is managed and how people take care of their bodies, right? These are very useful things that will impact millions of lives, potentially. And I would love to see that impact. I'd love to see our controls research to have an influence on how we understand neuroscience. And even beyond that, if this opens up new forms of robotics that just impact life here on Earth, that would be great too, right? It doesn't just have to be the singular quest of exploring other planets. But that is the real driver for these projects, is to build a robot that can go explore another planet. And all the rest of it is part of the benefits. And that's part of what NASA does. We explore the universe so that we gain all sorts of knowledge that gets used all over the place. Much of your technologies of your daily life are influenced by prior generations of NASA research.
I was wondering if you had a chance to check out Teo Johnson's Strand Beast exhibit at the Exploratorium.
I haven't seen it in person. I've seen lots of videos over the years.
You can see it in person now for the summer. Yeah.
I just heard this week about that.
So I noticed that it shares a lot of similarities.
Yeah. Very exciting stuff. I look forward to finding a time to do that. Thank you. Time, though, is one of the tricky parts.
Thank you. It's very fascinating design idea, but I am wondering how fast these things can be, and how energy efficient they can be, the locomotion. And also if they need to carry not just themselves, but some stable platform like sensors pointing at certain direction all the way or something like this. How can you achieve this? Thank you.
I'll attempt to answer your 4 questions. So again, energy efficiency-wise, one of the arguments, and we are not yet to the point, we're still figuring out the basics of how to control these, right? And so I would not claim that we are at the point of optimizing and maximizing their energy efficiency yet. I'd like to get there someday. But one of the theories is that if you can control a structure at its resonant modes, then you get the most energy efficient means of locomotion for that structure. And that's part of what we see in this combined flexible structure and rhythmic controllers, is that they do tend towards synchronizing to the resonant mode of the structure. And this is part of like how birds fly at a fraction of the energetics of our airplanes, right? Because they are working at a coupled resonance between the bird and the local environments, the bird's body and the local aerodynamic environment that it's in, which is also influencing. And so getting to the ability to figure out how to do that coupling of the dynamics from all the way from your control structure through the body to the local environment and make that one coupled system is, I think, the holy grail of efficiency. And I think this is hopefully part of the solution of getting there, right? I can't claim that I'm there yet, but I think it's a direction that will get us to very high levels of efficiency. Arguably, one little side amusing point is that we should be able to build a robotic horse that we can run with a 1 horsepower motor, right? So that just shows you how inefficient, that's how inefficient our current approaches are, all right? Locomotion speed, again, this is a design principle. I mean, Super Ball is going to be somewhat limited in its top speeds. In simulation, we had it going really fast at times, but it's, you're doing this sort of dynamic flopping and rolling. We haven't pushed it to the point of trying to get super, dynamic locomotions. Again, in simulation we have, and it looks nice and fun and fast, but we haven't built that yet in hardware. But again, it's a design principle, so I don't think there's any particular limitation to its ultimate speed. And then you would really start, if you really want to have a fast-moving robot, you start getting into the biomechanical design of it, right? Are you going to be using legs? Are you going to, what's the overall shape of the robot going to be, and how are you generating that power and force? Stability of the sensor platform. Yes, so this is going to be one of the interesting challenges, right? Right now we have this concept of putting a payload in this centrally suspended mechanism in the middle of the robot, and then you've got this rolling robot, and you're like, oh my gosh, I'm going to get really dizzy trying to drive this thing. And but there are a number of solutions I can imagine to that, right? One idea is you have a number of very small cameras around that payload, and you can do a virtual aperture, algorithm. This is stuff that's been done many times, where you create a synthetic single stable view out of a bunch of rolling, moving cameras. It's possible to do that, right? There may be other solutions for how do you manage the locomotion and navigation of the system. And again, there may be other approaches that we end up coming up with eventually that will give us the sort of the ultimate perfect hybrid, right? One thing that we have to remember is that when you're building an actual space system, you are always trading off different requirements, different optimizations against each other, right? So we may be losing certain forms of stability and management in the locomotion, but gaining this great ability to be robust to falls and slips and to be able to survive landing without an airbag. And so you may trade off some of these capabilities one for the other to enable sort of the perfect mission design. So these are all areas, though, that we're very interested in continuing to think about, and I just haven't had the opportunity to really tackle head on yet.
Hi. Thank you. That was a great talk. As a biologist who loves robots, this is a fun interface to see someone playing around in. But I think you may have probably already thought of this considering your closed loop thing that you were playing around with. But there was a C. elegans robot that was made, and it responds a couple years ago, and it will respond by itself to an obstacle, for example. So it runs into, and a C. elegans has a stereotype behavior to get around it eventually. And I'm wondering, because you may drop a robot in an environment, you may not know what's there exactly. Are you thinking about how you can get this robot to just respond to just an obstacle, for example?
Well, so in some of the videos that I showed, like where it was going over some of the lumpy, like the spine robot was going over some of the lumpy ground or some of the blocks and things like that. And even I had one picture here that was from some very early research when we were doing the spine robot. This one. Right, and we see going across these various terrains and the walls and whatnot. That was all done with no knowledge of the environment. That was all done as using this sort of reactive distributed control approach, where it would just run into these things and sort of eventually find its way over them. So I think there is a lot that can be done with that. And you can imagine, so it's if you just use your proprioceptive sensors, your sense of touch and your sense of feeling the forces and the things you collide with, you can figure out all sorts of ways to manage how to navigate through very complex situations. I have a 1-year-old son at home, and he's learning to walk, and he doesn't have a very complex planning algorithm around it. He just kind of like pushes and pushes until he eventually like crawls over my body and goes wherever he's going, right? And it works. It gets you there. The advantage of using things like your eyes, your other distant sensors, allow you to do things in a more efficient manner. It really optimizes how you spend your energy. Now you can, instead of like bumping into this and getting around it eventually, you're like, oh yeah, I could just walk around that. It'd be really easy, right? So you do your little motion planning, and it's more energy efficient and nicer on the skin too. So it's all about what level of capability you want to get to. But I think the important thing is that a lot of traditional robotics has started coming out of like a very industrial environment where you're like, I need to perfectly plan every single thing I do and have that controlled from that top end. We think about our tasks. This is what we are mentally aware of, are all the tasks that we want to accomplish. And so we've designed robots to do things that way. I think it's very important to actually throw that all away for a moment, start from the bottom up, figure out how do you make a system that is so capable and robust of interacting with the environment that you can do this, that you can bump into stuff and eventually find your way around it without breaking. Have that as your foundation. And now on top of that foundation, you start figuring out how to take that capability and plan for it and control it through a more complex, planned, intentional movement. And that's really going to be where you get the optimal balance of capabilities. But it means taking kind of a couple steps backwards relative to state-of-the-art robotics in order to make the big leap forward.
So please join me in thanking VITAS for an excellent seminar. Thank you very much.